Yes. Right. So welcome everyone. Thank you for coming to today's talk. This is the last talk of the PALS seminar this semester. The speaker today is Boney from Texas State University, and he'll be talking about building generalized indiscernibles in non-elementary classes with set theory. Thank you, Will.
All right. Thank you, Marcus, and thank you everyone for coming. I guess I was looking at the participant list, and it's a different crowd than I think I normally talk to, and that I kind of wrote this with maybe a more pure model theoretic crowd in mind. So if there are any questions, especially at the beginning as I'm setting everything up, feel free to jump in. I'd rather have you come away with understanding something than just sort of talk through results at the end. I guess I should also ask, when does the seminar end?
In an hour.
An hour.
Yeah.
Perfect. Yep. Okay. Yeah, I want to talk about building generalized indiscernibles. There we go. Sorry, I made the video screen really big, but let me make that small again. Okay. So we're going to talk about new adventures in an old theorem of Morley, although there's an asterisk here because the new really means in like 1980 is when that started. Then kind of talk about the main thrust of this, which is sort of the motivation to generalize the Erdős-Rado theorem. Talk about this weird thing that happened, and we'll give some examples of that and some motivation. Something weird happens with ordered graphs, which we'll talk about, and then we'll talk about how sort of large cardinals and forcing enter the picture. That's the using set theory in the title. So Michael Morley was one of the early great model theorists, arguably started classification theory by proving what was before known as Walsh's conjecture and his thesis, which kind of starts your career off with a bang. I want to talk about, though, one of his other theorems from a few years later, Morley's emitting types theorem, which says that the class of linear orders is minimal amongst large finitely accessible categories. Okay, of all the things in this talk that might sort of miss on this audience, this is sort of a joke because Morley was a model theorist. I don't think he might have said something like this later, but definitely not in like 1965. What he proved was, given a sentence in L omega 1 omega, where this is an infinitary logic where you allow countable conjunctions and disjunctions, it showed that it characterized when you have sort of arbitrarily large models. That if you have, what does it say? That if you have arbitrarily large models, although having models of size beta omega 1 is enough, then you can build what are called order indiscernibles. So for any linear order, you sort of build a model around that linear order that models this sentence psi, and the linear order is indistinguishable from the model theoretic properties of that model. With a little work, you can extend this. I don't know if he did this, but the proof is basically the same. Extend this to L kappa plus omega, where you allow kappa some infinite cardinal, you allow conjunctions and disjunctions of size up to kappa, and it has models of size at least to kappa plus.
This result is due to Tiffany Chang from 1960.
Chang is the one that
it's from modern point of view, you could say it's the same proof, but it wasn't in antiquity, and it deserves much credit, I think, for this.
Okay, so Chang extended Morley's proof, and I should also add that, I called this Morley's emitting types theorem and Chang's generalization of it. We don't see emitting types here, but I guess another result of Chang says that these classes with axiomatized by infinitary conjunction and disjunction, you can change the language in some inessential way and turn it into a type emitting class. So it's basically saying if you can emit types up to some big enough threshold size, then you can build these order indiscernible models, or models generated from some order indiscernibles that also emit those types. This is really nice. It gives you it computes the Hanff number of these classes, for instance. But this phrasing at the very beginning comes from Mackay and Perret, who have this great book about accessible categories and the ways in which accessible categories sort of when you do model theory, essentially, the class of models with embeddings forms an accessible category. And so how did they phrase Morley's theorem? The category of linear orders is minimal amongst the large finitely accessible categories. What does minimal mean? Minimal means that if K is a large finitely accessible category, then there's a faithful functor from the category of linear orders to K that preserves directed colimits. Right, and as I said, this is a weak attempt at a joke. Pity laughter is always appropriate, not just here, but at any point throughout the talk. If you think I'm making a joke, it's okay to laugh a little bit. And so what I want to do is I want to take this phrasing of Morley's theorem and kind of push it farther. And I want to find sort of other minimal categories and talk a little bit about sort of what we can do with them and why I'm interested in them. And sort of as I try and describe myself as a researcher, I think of myself as like a model theorist whose work intersects with set theory and category theory. And this project is really like kind of checks all those boxes for me. The category theorist really likes the way that Mackay and Perret phrase this in these slick diagrammatic ways. Set theory comes in and how you can try and find these minimal categories. And the model theory comes in with sort of what you can do with them, which is less the focus of this talk, but also very interesting. Okay, so to motivate this a little more, I guess first I want to unpack sort of Mackay and Perret's phrasing a little more. And I'm going to start with a little notation that we're going to use throughout the talk. So rather than keep saying the class or the category of linear orders, I'm going to use the script K to the OR. Or stands for order. Generally, script K is going to be some kind of like index category that I'm going to try and build indiscernibles indexed from. So like linear orders, ordered graphs, trees, stuff like this. This boldface K, and it's unfortunate that I'm just using K everywhere, but I guess I learned it from my advisor, and so you can blame Rami. Wagging his finger at me. But the boldface K are sort of the target categories where indiscernibles are supposed to exist. So you should think of these as categories indexed by some L infinity omega theory you like, or an abstract elementary category, or to be the broadest, some category that admits a faithful functor from finitely accessible categories. I forget if I say this in a second. Yeah. So then let's unpack this a little more and create kind of a dictionary between model theory and category theory. So Mackay and Perret talk about finitely accessible categories. And you should think of those in your head as classes axiomatized in L infinity omega. They're not exactly the same. There's some extra stuff to add here. I guess the precise way of saying this is any finitely accessible category is equivalent to one axiomatized by some L infinity omega theory. And it's not the case that any L infinity omega theory is finitely accessible. Basically, you don't know you have finitely generated objects. But if you scolemize it, then you get a finitely accessible category. And we're going to be scolemizing all over the place. So that's fine. Mackay and Perret also said large. That just means class many models up to isomorphism, which also just means arbitrarily large models. And so then there was this idea of there should be this faithful functor preserving directed colimits from the class of linear orders into the target category, the AEC or whatever. And the model theory should think of this as blueprints that build order indiscernibles. And I kind of want to unpack this a little more. So a blueprint for order indiscernibles is really like, it's a blueprint. It's like a set of instructions that has some language inside of it. And it tells you how to take a linear order I and build like a structure from it. That there are a bunch of functions in the language. So the universe starts out as all of the terms in that language applied to your elements of your linear order. But then the blueprint also tells you when terms should be equal and when relations should hold of terms. And that's kind of all of the information you need to build a structure. And so why does this give us this sort of faithful functor? Well, these instructions, if you unpack what this means, are faithfully functorial. So if I like take an embedding from I to j between two linear orders, the instructions on j, when I restrict them to I, just tell me to do what I'm supposed to do on I. So to map from I to j, lift to a map from em I phi to em j phi. Em here stands for Aaron Fuchs-Mostovsky, who sort of developed this theory, I guess in the first order case with orders. And these instructions are finitely generated. So because you're taking terms of finite tuples from your linear order. So this EM construction kind of commutes with increasing unions of linear orders or directed colimits. And this is what it means to preserve directed colimits. So sorry, I'm trying to move these bars to where they're not in my way. So Mackay and Paret's observation is that, right, any blueprint generates this sort of faithful functor that preserves directed colimits. With a little work that can be reversed, John Baldwin and I actually had this discussion, right? I say as would be phrased by Mackay and Paret. I don't think we knew enough category theory at that time to phrase it, but we had some argument that essentially said that if you take any faithful functor, sort of on and restrict it to the finite linear orders, you can kind of lift this to a blueprint that works with your category K. And so what this tells us is that blueprints for order indiscernibles in K are exactly directed colimit preserving faithful functors from the category of linear orders to K. And there's this extra technical condition that is not super important, that I should probably just remove. So that's kind of the big key observation that we want to start with. And it sort of leads us to some natural questions that we'll discuss. So can we do this with classes other than linear orders? What can we do with these sort of nice functors once we have them? And right, I advertised set theory in the beginning. What does this have to do with set theory? So now we're going to talk about sort of generalizing the Erdős-Rado theorem, or generalizing this idea of indiscernibles. So we have this way of phrasing indiscernibles indexed by linear orders. But generalized indiscernibles, you want to index them by stuff other than linear orders. And you can write this out in sort of a very model theoretic way with kind of types and everything, but there's a lot of notational complexity that's simplified by approaching it category theoretically. Misha Gavrilovich has this sort of nice way of indexing it that sort of uses the simplicial category. But the way we've set it up, it's sort of much easier, right? So a blueprint for order indiscernibles in K is just a colimit preserving faithful functor from the class of linear orders into K, into bold K. So to make this work for some other index category, I just swap that out for the category of linear orders. So fix some script K, probably some simply finitely accessible category, very likely like a universal class or something. So a blueprint for K indiscernibles is just a colimit preserving faithful functor like this. Easy peasy mac and cheesy. Pandy Cat is one of the characters in a show that my children watch that has invaded my life. So now it invades your life as well. But so this, category theory lets us make this really nice, slick definition of what it is to be a blueprint for generalized indiscernibles. One phrase Rami said to me once that I've always remembered, I'm really picking on him, maybe since he's in the audience, is that definitions can't be wrong. But maybe to be useful, it's nice to actually have like examples of when you have these, when you can build these sort of directed colimit preserving faithful functors. And again, right, if we go back to just linear orders, this is exactly what Morley's omitting types theorem tells us, maybe with this extension by Chang, that, yeah, what it's really saying is that if you have models of size at least bet sub 2 to the kappa plus, then you can build a blueprint from the class of linear orders into models of T. And so how do you do this? You use the Erdős-Rado theorem. That's where this is coming into everything, right? Which is this nice sort of generalization of Ramsey's theorem to the infinite context. It tells me that if I'm fixing some finite number k and some infinite cardinal kappa, I want to color some set with the k tuples from it with kappa many colors, and I want to guarantee that I get an infinite homogeneous subset of size kappa plus. The Erdős-Rado theorem says I have to start with a set of size at least bet sub k minus 1 of kappa plus. And this is sharp. There are some examples here where if you drop this plus here, it's false. Right, so I kind of want to outline how this proof goes. There's kind of a dream construction that we'd really like. And it goes through more the model theoretic side of things. But so you start with some big structure M and a big subset of it, and you kind of want to build indiscernibles patterned off of this big subset X. So we're going to do an inductive construction where we find sort of k indiscernible subset of X for each k. And if we put them all together, this is what our blueprint is. So base case is 0 indiscernibles, that says nothing. So anything is a set of 0 indiscernibles. So if the inductive step, if I've got a large set xk that are k indiscernibles, I can color the k plus 1 tuples from it by their type. Okay, so that's a coloring. I can use the Erdős-Rado theorem to find a homogeneous subset xk plus 1. And the homogeneous sets for this coloring, these are exactly k plus 1 indiscernibles, right? I've colored them by their type, so their type is all the same. You just do this omega many times and you get your indiscernible blueprint. And so you might ask, well, this is great. And you want to know like how big is big, because big was very vague here. Although I guess in the statement of the theorem, I kind of gave away that it's like bet sub 2 to the kappa plus. But you wonder where that comes from. So you kind of look through the proof and see what you need. So you need to take xk and shrink it to a homogeneous xk plus 1 through a k plus 1 coloring. So the Erdős-Rado theorem tells you that the size of x sub k has to be at least bet sub k of the size of xk plus 1 plus. Unfortunately, that means that these sets have to be decreasing in size. And that gives us an ill-founded sequence of sizes. And that's very bad. You can't have that. So there's actually an ill-founded nightmare. But you can fix it. The idea is that instead of this just like one linear chain of decreasing sets, somehow you build this tree of approximations. And the tree is well-founded, so you don't get this kind of ill-founded, or the tree doesn't have any infinite branches, so you don't get this ill-founded sequence. But it also has height omega, so you can kind of get as far along as you need in it. And the indiscernibility is kind of shared across the levels of the tree, so everything works out great. Actually, Jerzy Rositzky has a nice argument that kind of makes this tree idea explicit and removes a lot of the technical bookkeeping. There's also a way to do this argument where you like move to an ill-founded model of set theory. But I have never really liked that argument. So I like to emphasize this one. But in the end, kind of as we advertised, you need to start with a set of size at least bet sub 2 to the kappa plus, where kappa should be like the size of the language, or really the size of we're skolemizing, so the size of the language after skolemization. So if it's an AEC, this is the Lowenheim-Skolem number. Okay, so this is how it works for linear orders. How do we get generalized blueprints? Well, again, maybe a definition can never be wrong. So call script K an Erdős-Rado class if it's minimal amongst these large finitely accessible categories. So if for all large finitely accessible categories, there's a co-limit preserving faithful functor. This is the category theory definition of it. There, you can phrase this model theoretically as well, and you can get a little more information from that. But that's sort of a detail that I'm skipping over for the talk. But to actually prove something is an Erdős-Rado class, we need something like the Erdős-Rado theorem. And this brings us to the idea of like a structural partition relation. Right, maybe, so in first order logic, right, you use the compactness theorem to build indiscernibles. And so you don't need these infinitary versions, you just need like the finitary Ramsey's theorem. And so in first order logic, when you build generalized indiscernibles, you need sort of a structural Ramsey's theorem, which is this whole theory of Ramsey classes that has popped up. And there's a lot of great study there. To do this for finitely accessible categories, infinitary model theory, whatever, you need some structural version of the Erdős-Rado theorem. And that's kind of what I want to talk about now. But before we define exactly what that is, I want to kind of start with a cautionary tale where you have to be careful in how you define this. So we're going to start with maybe the first thing you think of past the class of linear orders, K2 OR, which is the class of two linear orders. Okay, so I0, I1 is in K2 OR if there's some linear order that kind of orders them each separately. Maybe for definiteness, you say that everything in I0 is less than everything in I1. But you have this partition of your linear order. And so I'm going to define a coloring, which for some reason, I made this a 3 coloring, but I only use 2 colors. But basically, you're going to color pairs by looking at whether or not they're in the same partition. So given I and J, we're going to color the pair 0 if they come from the same partition, and 1 if they don't come from the same partition.
Or the second I is the J?
Yes, that should be I is in I naught if and only if J is in I naught. Thank you. Otherwise, it's a much more boring coloring. Okay, so this is a great coloring. And right, so some version of the Erdős-Rado theorem should say we have a big homogeneous subset.
Oh, so why it is coloring in 3 colors, coloring in 2 colors?
Right, yeah. Well, 2 is less than 3, so it's also a 3 color.
So it's a mistake that you wrote 3, or you intend to?
No. This was just like a typo.
Okay.
I think maybe the first round I like put it in 1 if they were both in I0 and 2 if they were both in I1 or something. And then I removed that but forgot to change. Whatever. It's a 2 coloring. So the problem here, though, is that you can never get a completely homogeneous coloring that contains sort of big stuff from both of your parts. Because, right, if you have 3 elements, at least 2 of which are in different partitions, then you've got 2 things in the same part. So you've always got 0 represented, and 2 things in different parts. So you've always got 1 represented. And the problem is that when we move beyond linear orders, we kind of have more information to use to color the types, right? If you give me, right, like an in-element subset of a linear order, there's kind of only one way they can arrange. Okay, you insist that they're increasing, and then that's all you can say about it. But when you add more structure, there's more information about how those elements in the index models are related. So you need to sort of include that into your coloring. And so because what we're essentially doing here is we're using the type of the pair to color them, we can't expect 2 elements of different types to be made to have the same color. So instead, we have this idea of type homogeneity, where the coloring is not a single element, but the coloring only depends on the type of the inputs. And then there's this other aspect where if we just look at the cardinality of the linear order, we can't force sort of I0 and I1 to both be represented in there. So instead of talking about the cardinality of the element of K2 OR, we want to talk about how universal it is, which in this case says that, you know, you're kappa universal if and only if each of your parts are at least of size kappa. And so there you get this like different notion of what it means to be big kind of from the index class that you're looking at. And so there's this nice quote here from Heinel and Larson, I think in their Handbook of Set Theory article on partition relations, basically just talking up the partition relation symbol and how great it is. And so I define this sort of structural partition relation. It's different than the one you see in Ramsey classes because these are all cardinals rather than like finite structures. But basically, lambda k arrows kappa to the n mu, if any time I take a n coloring of M with mu many colors, that's lambda less than lambda universal, replacing of size at least lambda, then I can find an embedding from n into M, not of and I don't require that n is of size at least kappa. I instead require it's less than kappa universal. That's my stand-in. And I want that this subset of M that's induced here is, again, not homogeneous, but type homogeneous. The coloring of a tuple from N depends only on the type of the input. Okay, and so the following, right, and so how does this relate? Erdős-Rado, this sort of structural partition relation relates to Erdős-Rado classes in the same way as the original Erdős-Rado theorem does to linear orders. That if it's the case that for everything you plug into the right-hand side, there's some lambda that makes this whole thing work, that proves that script K is a combinatorial Erdős-Rado class. And the proof is just morally the same argument as before, but with a lot more bookkeeping. I feel like this is a case that's happened, right, where like you stare so intently at a proof that like it seems obvious, but it's not obvious. It's very technical and there are a lot of steps. But once you kind of stare at the proof of Morley's emitting types theorem long enough that it becomes obvious, the proof of this theorem kind of falls out. But there's a lot more bookkeeping to do. What happens sort of in general, and we'll see some examples in a second, is that this lambda is, right, for the Erdős-Rado theorem, it was bet sub n-1 of kappa plus. Typically, it's bet some polynomial of kappa plus. And there's a lot of kind of wiggle room for getting that bet sub 2 to the kappa plus threshold that we saw before. And so, you know, even if this is like bet sub omega or even larger, you still don't kind of mess with this threshold at all. So what are some examples? So, right, linear orders, obviously, the Erdős-Rado theorem says that this holds for them. We can also talk about chi linear orders, where chi is some potentially infinite cardinal. So you have disjoint linear orders that you want to kind of like simultaneously keep big. Erdős, Heinel, and Rado showed that this partition relation holds with this polynomial being n squared plus n. Of course, I mean, they didn't use this vocabulary, but this is what they showed. You can shift this a little bit to convexly ordered equivalence relation, which basically what this means is you have these disjoint linear orders, but instead of being indexed by some chi that's fixed from the outset, you have another parameter set that indexes these linear orders. And that parameter set can like grow and shrink as you change your model. And so if you use this Erdős-Heinel-Rado result several times, you can show that this partition relation holds for these convexly ordered equivalence relations. There's also this result of Grunhut and Shalad that if you take well-founded trees, they have a really nice partition relation. I like to point out this example just because somehow this threshold cardinal is much, much bigger than any of the things before. Right, so bet sub n means that you iterate the 2 to the operation n many times. Oops. Bet sub 1n, instead of iterating the 2 to the function, you iterate the bet sub 2 to the plus, this sort of Hanft number threshold. You iterate that in many times. So this gets very big very quickly. There are also, you can also build blueprints from trees of finite height or height omega. Shallah, in the index for his like first order classification theory, has some nice combinatorial result for trees of height n, for n less than omega. And then there's this interesting thing that happens at sort of height omega, that you don't have the combinatorics here, this sort of structural partition relation, but you can still build blueprints from the class of k omega trees. Sort of you take your tree of height omega and you kind of iterate, cutting it off at height 1, building 1 indiscernibles, then extending it to height 2 and building 2 indiscernibles, using the fact that K2 tree has this structural partition relation. And you kind of interleave these steps all the way up to get blueprints from trees of height omega. Yeah, and so these are some great examples. I'll kind of briefly mention examples because I mainly wanted to talk about the set theoretic construction. But the reason I really like these things as a model theorist come from like 2 directions. The first, and I'll give an example of this, is that they let you sort of, right, when you leave first order logic, when you move to AECs, you lose compactness. But I'm very interested in kind of like the fragments of compactness that you can get back somehow through set theory, through model theory, through algebra, however. And one of the things that these generalized indiscernibles do is that they let you kind of mimic certain proofs in compactness. And so I'll talk about that. Then there's this idea of defining dividing lines via indiscernible collapse that I'll also talk about in a second. So what is the compactness story? So Shallah has this great result from first order classification theory that one of the following holds. That is basically you're either super stable or strictly stable. That you're stable on a tail of cardinals starting no later than the continuum, or you're unstable in every cardinal where lambda is less than lambda to the omega. So how does he prove this? He builds what are called Shallah trees. I know this name appears in John's book. I don't know if it appears before that, but it's basically you have this tree indexed by lambda to the less than omega of parameters, and as you go along each branch, the types that you get along those branches are different, and they're witnessed by sort of wherever those 2 branches met, or whatever the last place they split was. And so what's the difficulty here is showing that if you're unstable in one cardinal like this, you're unstable in every cardinal like this. So you can write down for a cardinal mu the first order theory that axiomatizes a model of T with one of these Shallah trees indexed by mu to the less than omega. But you have to show this is consistent. If you know it happens once, then you know that theory is consistent for some lambda. But compactness says that all of these the finite parts of all of these theories look the same. And so if it's true at one lambda, it's true at every lambda. And so having a Shallah tree in one cardinal lets you kind of move it around to have a Shallah tree at every cardinal. And this gives you instability precisely when you have this cardinal arithmetic. Okay, so this is a beautiful use of compactness that it kind of seems like when you move to infinitary logic, you sort of lose completely because you don't have compactness. However, you can show, Baldwin and Shallah did this for like atomic classes. I was able to extend it to Kappa-Tame AECs with amalgamation. that you get this sort of same result. Okay, you replace the continuum by the Hanff number, but you get the same dichotomy of stable on a tail starting at some expected cardinal, or unstable in every lambda to the lambda less than lambda to the omega. And the proof is really the same, but instead of compactness, you use the fact that K omega trees is an Erdős-Rado class, and you say, all right, if I have this at 1 lambda, I can't write down this theory nicely anymore, but I can pattern indiscernibles off of this Shalot tree in such a way that when I plug in other mu to the less than omegas, I get Shalot trees of those different sizes. And so the details here are not like super important or super fleshed out. The idea is that we lose compactness when we move to infinitary logic, but these generalized indiscernibles can help us kind of retain some of this compactness. And I like to contrast this with, I don't know, this is a result of, I guess, several years ago now from Sebastian Basie. And I just sort of contrast this because he was proving this purely with sort of forking calculus, other methods, and has something sort of similar, that you're Galois stable on a tail, or you're unstable in every sufficiently large lambda with, okay, now he has Kof lambda instead of this cardinal arithmetic, and some other cardinal arithmetic going on. That you get sort of, so this is, Basie's result is what I would kind of consider the state of the art from forking calculus. But these generalized indiscernibles give you kind of an improvement on that through, I would also argue, sort of much easier techniques. Now, his techniques do a lot of other things as well. I don't want to, you know, I'm not going to be the one to speak ill of Basie's work. But I just wanted to contrast this as like a nice application. Okay, so that brings us to ordered graphs, and sort of this idea of indiscernible collapse, right? So I mentioned ordered graphs at the very beginning, but I didn't say in my list of examples whether or not they're an Erdős-Rado class. And this is a really important one because these are well studied amongst elementary classes, right? In classification theory, there's this whole library of dividing lines that are important and that sort of we often try and generalize in some way or another to abstract elementary classes. One way that you can characterize these dividing lines, or at least many of them, is through this idea of indiscernible collapse. So this is the one for NIP theories that uses ordered graphs. This is due to Linsko, that T is NIP. So what's the diagram here? KOG is the class of ordered graphs. There's this forgetful functor down to the class of linear orders that just forgets the graph structure. And as we've said, an ordered graph indiscernible should be a co-limit preserving faithful functor from KOG into mod T. And NIP theories are exactly those that whenever I have a blueprint phi like this, I can sort of factor it through the class of linear orders. This is called indiscernible collapse. You build these ordered graph indiscernibles, but the graph part of the index structure doesn't matter. It just sort of collapses down to an order indiscernible. The most famous of these coming before this, of course, is Shalot's proof that stable theories exactly correspond to theories where ordered indiscernibles collapse into set indiscernibles. And so, yeah, I like, this is kind of the thing that first brought my attention to this idea of generalized indiscernibles, because it seems to suggest a way of generalizing these notions to AECs that, I don't know, that seems less bogged down in the particulars, that you're not talking about counting types. Okay, then I worry about amalgamation and all this stuff. You're just talking about kind of indiscernible collapse. And so it suggests a way to generalize the notion of NIP to AECs. You just argue the same, you just use the same kind of indiscernible collapse. I call K NIP if every blueprint, if every ordered graph indiscernible factors through this sort of linear order indiscernible. And Wintao Yang has some other notion that's sort of more local, kind of more in the style of counting types. Okay, but this definition is great, but it only actually means anything if there are ordered graph indiscernibles in K, right? Otherwise, it's a vacuous universal quantification. Every AEC is an IP, and it's kind of a useless definition. So Rami, you're raising your hand.
Oh, yeah. Is your definition equivalent to his?
I don't know. Wintao and I are trying to find a time to talk, but I keep delaying. I think so. His is much more local, right? Because it's about like the behavior in one cardinal. I'm hoping there's some connection though.
So it could be a different notion.
So it's definitely like different notions as stated.
Yeah, no,
it
but
could
if
be
you
the case.
show some cardinal lambda above the Lovenheim's column number, then I mean this is a case to check. So they may be different.
Yeah.
At least as far as you know. Okay, thanks.
But yeah, so we need to know if there are ordered graph indiscernibles. So we've reduced this to another question. Is there a partition calculus for the class of ordered graphs, some kind of Erdős-Rado theorem? And the answer is maybe. And I guess like all good maybes, it has to do with set theory and consistency. So it's the history. So a bunch of different people proved essentially that ordered graphs are a Ramsey class, but that's great for first order model theorists, but not enough for me. So you want to know about kind of infinitary versions. So Erdős, Heinel, and Posa proved that for sort of omega in the right-hand side, there's a nice partition relation that for any countable, yeah, what you see there, at least for pairs. Unfortunately, Heinel and Komjath show that it's consistent with ZFC, that it fails at the uncountable case. And there's some omega one size graph where you fail this partition relation. And their proof is not super important. On the other hand, why is it maybe? Because Shallah proved that it can consistently fail. That's what Heinel and Komjath proved. But Shallah proved that it can consistently hold. That for all H and all kappa and all N, there's some G such that we have this nice partition relation. And he also did this not just for graphs, but for colored hypergraphs, let's call them. Heinel has some other interesting results. But okay, so we got to this maybe. There's this nice part. Maybe there's a partition calculus. Maybe there isn't. But I don't know, maybe this feels like a bait and switch. I asked about indiscernibles. I said you should really think about partition relations. Then I said partition relations or maybe, but now I'm going to tell you that I don't really care about partition relations. I care about ordered graph indiscernibles. And so I want to unpack this proof a little bit. So then we're going to talk about two ways you can kind of get more information out of it. So as you do, so you assume you have GCH for some nice initial combinatorics. Fixing some mu, you come up with this forcing P mu that kind of, you want some global coloring result. So you force with P mu to take care of all graphs of size less than or equal to mu. These P mu's are very simple. They're partial functions from some kappa and from kappa into 2 of size less than mu. The important thing that will come up later is it's less than mu directed closed, which means if I have a, right, they're just partial functions. So if I have a collection of partial functions that is a directed set and the whole thing is of size less than mu, their union is in the forcing. And I have this parenthetical sort of that just means there's some like, you don't actually force the full coloring, you force an inhomogeneity result. And then you iterate all of these P mu's together to get this sort of result everywhere. And then you want just a full coloring relation, full sort of homogeneous coloring relation, and you can iterate in homogeneous relations to get the actual results. Maybe that's not super useful because I didn't tell you what inhomogeneity was. But the idea is that you iterate a bunch of forcings that are all very directed closed. Okay, so let's take this now and let's go off to infinity and beyond. So the first stop, large infinity, is large cardinals. And so you have this. So what is this proof? It says that if you have a certain large cardinal, you can get kind of a Ramsey style result. That if kappa is Laver indestructible supercompact, then you have sort of, maybe it's easier if I mention it here, sort of kappa arrows kappa to the n less than kappa. That if I take any kappa sized graph, I color it in tuples with less than kappa many colors, I can find some less than kappa universal subgraph of it that's type homogeneous. Basically, the way this works, again, skipping some of the details, you do this forcing from Shallah sort of starting above your indestructible supercompact. Because it's indestructible, it's still supercompact. So you can kind of reflect this coloring result down below it. And then you get this nice coloring sort of below kappa. That's what you want. But the key aspect of being less than mu directed closed forcing is that you don't add any sets of size less than mu. And so once you've reflected it back below kappa, you couldn't have added it by forcing. So this homogeneity embedding had to be in the ground model. And so that gives you this nice Ramsey cardinal result. And so if you had a Laver indestructible supercompact, you could build blueprints as you normally do. And this works anything you can force to make this partition relation hold in a sufficiently directed closed way. And there's some work in progress to kind of figure out exactly what those classes are. But so this is one way to sort of extend this result, is to take a large cardinal and you get this nice sort of Ramsey result, and then you get a lot of ordered graph indiscernibles. But then you kind of have to, before we are looking at like bet sub 2 to the kappa plus as this threshold, and now we're shooting up to some very large cardinal. So that's nice, but not ideal. But luckily we can do better. And this is the beyond part. And this kind of brings us back to the very beginning of thinking about what blueprints really are. So there are these, everything here is class size. So there's some definable functor between class-sized objects. But really, they're generated by, since they're co-limit preserving, they're generated by what happens on small objects of script k, right? I write k less than mu for some mu, but if k is finitely accessible, mu is omega. These are all finitely generated objects. So even though, right, you might be built around rank bet sub 2 to the mu plus, right? This is the threshold we need to run these Erdős-Rado arguments. The blueprint itself, the thing you build in the end, lives much farther down, lives in some v kappa plus omega, or mu plus omega. Maybe the sort of thrust of this argument is easier to see with model theory, that blueprints are really just functions from types over the empty set in one class to types over the empty set in another class. And these aren't maybe they're Galois types, but really in practice, they're just like quantifier-free types. So the only thing that's making these big in rank is like the size of the language. Otherwise, they sort of, even though you're going way up to build them, they exist very low down. And so we get this nice, we can read out of this Shallah forcing result that without any large cardinals, these classes, ordered graphs, colored hypergraphs, are almost Erdős-Rado classes. That is, we can build these blueprints into any large K, large finitely accessible K. This parenthetical almost, there's some pieces that we're missing to kind of make this precisely Erdős-Rado, but those were the pieces that I suppressed earlier. So But basically the idea is you do all of these forcings that we've described, but you do them all in sort of a sufficiently directed closed way, starting at some, I don't know, chi above where your blueprints would live. Then you work in this forcing extension where you have nice combinatorics. You use whatever generalized Morley's emitting type theorem to build blueprints in the forcing extension. But because the rank is low, these blueprints already had to exist in V. Okay, but maybe they're not actually blueprints in V, but if you run through the definition of what it means to be a blueprint, it's like delta 1 in the parameters. So it's absolute between all of the models that you're thinking of. And so you go from, so without having the combinatorics in the ground model, you can kind of go to some nice forcing extension where you have the combinatorics, build the blueprint, but because your forcing was nice enough, that blueprint already had to live in V. So somehow you've used forcing to prove this ZFC result, which is always nice and interesting. Okay, so then, right, that's sort of the end. I want to mention briefly some questions or works in progress. So I mentioned kind of this idea of what's beyond colored hypergraphs or ordered graphs, that like, what can this Shallah result about forcing these combinatorics be extended to? This is some work in progress we're working on. Then kind of thinking more about applications, this lets you define a bunch of sort of dividing lines through indiscernible collapse. Like, what can you do with this? How far can you push this? And there's a lot of open questions here. And then finally, kind of at the end, I mentioned, right, we have this interesting thing where we do some forcing, but we get a ZFC result. We do forcing to build something in the ground model, which is always kind of weird. And it makes you wonder if you can do this proof without forcing. And there's this interesting result of Heinel that I made passing reference to that suggests an approach, but it's only a suggestion. All right. Well, thank you. And yeah, are there any questions?